What is machine learning? Herbert Simon, an American economist and cognitive psychologist, defined learning as a process by which a system improves its performance from experiences. Tom Mischel, a Carnegie Mellon University professor in computer science and a long contributor in machine learning and expertise in artificial intelligence, defines machine learning as the study of algorithms that improve performance P at some task T with experience E. So P, T, and E, performance, task, and experience, these are going to be the components that define machine learning. You may be wondering what is the difference between programming, traditional programming that we know it, and machine learning. To put it in a simple way, in traditional programming, we give the data to the computer and tell it what to do and how to do things for us. And the computer simply listens to us and follows the order and performs the task that we want it to do in a very efficient way and gives us the results. Not very intelligent. Actually, the intelligence comes from us, not the computer. In machine learning, however, we give the data to the computer and tell it what we want. This is especially true in supervised learning. And the computer has to learn by itself how to do to get the output that we want from it. So the computer has to play an intelligence role here, not just follows simple tasks. Arthur Samuel defines machine learning as a field of study that gives computers the ability to learn without being explicitly programmed what to do. When and where to use machine learning? Machine learning is used when human expertise does not exist because, for example, exploration or navigation is unaffordable or dangerous, such as navigating another planet, or where human cannot explain their expertise. For example, in speech recognition, you can definitely recognize your mom's voice, but could you explain that skill to someone else and teach him how to recognize your mom's voice? Or when models or products, for example, need to be customized for the endpoints at the consumption, personalized medicine is an example of that, or when models have to be based on huge or lots of data, such as in genomics. But learning is not always useful or even necessary. For example, for a simple task such as calculating payrolls, we don't need machine learning. A classical example of a task that could use machine learning is handwriting recognition. In handwriting recognition, similar to voice recognition, we can't really explain how to recognize someone else's handwriting, even if we ourselves know and are capable of recognizing someone else's handwriting. Therefore, handwriting recognition is a perfect task for machine learning. Let's see more examples of problems that can best be solved by machine learning. Machine learning can be used in recognizing patterns. For example, recognizing facial identities or facial expressions, or handwriting or spoken words, which are already talked about them, handwriting and speech recognition, or in reading and analyzing medical images, For example, to identify whether someone has tumors or not, identifying tumors, recognizing tumors in the early stages. Machine learning can also be used in recognizing anomalies. Anomalies are strange data values that do not conform to the overall pattern or structure. An example of anomaly is outlier. For example, machine learning can be used to track unusual credit card transactions for potential fraud activity. Machine learning can be used for predictions. For example, future stock prices or currency exchange rates. Defining the learning task. So we learned that machine learning can be defined as improving on task T with respect to performance metric P and based on experience E. Examples of these can be, for example, the task can be recognizing handwritten words. The performance for this can be the percentage of words that are correctly recognized or classified. The experience here can be the database of human labeled images of handwritten words. Another example, the task can be categorizing email messages as spams or legitimate emails. The performance here would be the percentage of email messages that are correctly classified as spams or legitimate emails. The experience here would be the database of emails, some with human given labels as spam or legitimate. Let's see some state-of-the-art applications of machine learning. An example would be autonomous cars. You might have heard about some companies that are working on making cars that can drive by themselves without any need for a human driver, such as Uber or Tesla or Google. The autonomous car technology has to control all the movement of cars, including speed, steering, and brakes, and also has to recognize traffic and pedestrians and avoid engaging in any accidents. Another example would be a speech technology in some smart assistant systems, such as Google Assistant, the Microsoft Corona, the Apple Siri, or Amazon Alexa. These systems have to understand spoken words and respond to them in an intelligent way. Types of learning: supervised or inductive learning. Supervised learning is the most common type of machine learning. Supervised machine learning algorithms are designed to learn by examples in a process that is called training, given input data that are labeled, meaning the input data are matched with their corresponding outputs. We call these data labeled. During the training process, the algorithm must search and identify hidden patterns and relationships between the pairs of input data. This process kind of mimics learning for the algorithm, learning the patterns or the relationships. After the training process, the trained algorithm will be given an unseen set of input data that is not labeled, meaning we don't really know the corresponding outcomes or outputs for these data. The algorithm has to determine the appropriate label for this data based on the training that it has had. So the objective of supervised machine learning models and algorithms is to predict the correct label for newly presented input data. In this course, we're only going to cover this type of machine learning. Next, we have the unsupervised learning. Unsupervised machine learning algorithms have to infer patterns and relationships from a dataset without any reference to known or labeled data. Unlike supervised machine learning algorithms, unsupervised machine learning algorithms do not have any reference or guidance because they do not have any prior knowledge or labeled data. Next, we have the informed learning. Reinforcement learning is a type of machine learning algorithms that work in a sequence of decisions in which the algorithm has to learn how to achieve a goal in a complex environment in a game-like situations, and it has to employ trials and errors to come up with a solution to the problem. In this process, the machine gets either rewards or penalties for its actions and performances. The goal for the algorithm is to maximize its total rewards. You might have already heard about deep learning and may be wondering what's the difference between the two, the machine learning and deep learning. Deep learning is considered an evolution of machine learning. It uses a programmable algorithms and methods such as neural networks that we're going to learn about later on to make accurate decisions without any help from us humans. For example, in deep learning, the feature extraction that is used in a classification algorithm that humans otherwise would have to specify and extract them would be done by the algorithm itself. For example, suppose that we want to design a classification algorithm such that we give them the car, we give the algorithm the car, and the car would specify different, classify the cars. So in this process, it is up to us, the humans, to extract a feature that can be used to distinguish cars from each other. For example, the shape of the car, the model of the car, the number of doors, the number of cylinders, or any other features that are important in distinguishing and classifying cars. This process, finding and extracting features, has to be done by the algorithm itself in deep learning. Machine learning in a nutshell. There are already thousands of machine learning algorithms, and probably hundreds of new algorithms are invented each year. But there are some commonality and common grounds between these different algorithms. Every machine algorithm has three components. First is representation. How to represent knowledge or type of algorithm. Choose a feature to represent. Next, we have the evaluation. What criterion to choose to evaluate the performance of your algorithm. And next is optimization. Choosing the best parameter or set of settings for your algorithm to yield the best performance of it. Various function representation. There are different types of representation in machine learning. We have numerical function representation. Examples of these are linear regression. We have artificial neural networks and support vector machines. We have symbolic functions. Example of these is decision trees. We also have instance-based functions. The example is nearest neighbors, such as k-nearest neighbor. We also have probabilistic graphical models. Example of these is the naive Bayes method. Generally, a machine learning algorithm in the learning process consider and inputs a set of samples of data and then tries to predict properties of unknown data. If each sample is more than just a single number, and for instance, a multi-dimensional entry as we have in multivariate data, it is said to have several attributes or features, as you see in this table. For example, the student ID, first name, last name, major, year, etc. These are features or attributes. Learning problems. Learning problems fall into a few categories. The first of them is supervised learning. In supervised learning, data comes with additional attributes that we want to predict. The problem can be either a classification problem in which samples belong to two or more classes, and we wanted to learn from already labeled data that we know what classes they belong to how to predict the class of unlabeled data in which we don't know the class of the data. An example of a classification problem would be handwritten digit recognition, in which the aim is to assign each input vector to one of the finite number of discrete categories or classes. That's why it's called classification. The next is regression models. When the output consists of continuous variables, such as predicting the length of a salmon as a function of its weight and age, it's called a regression. You're already familiar with regression from statistics. As we have learned so far, one type of supervising algorithms is classification algorithms. There are two types of classification algorithms: binary classification and multi-class classification. In binary classification, there are only two classes or two labels. We use a labeled sample data to train our algorithm. The algorithm is usually called a classifier to learn the hidden relationship in our data. And then after the training process, the classifier will be given an unseen new set of data that is not labeled. And the goal of the classifier is to classify and label the data correctly. A familiar example for this type of classification is a spam detection in your beloved email service, such as Gmail, for example. In this example, the classifier has to learn how to distinguish a spam from legitimate email so that it could put the spams in the spam folder and put the legitimate emails in your inbox. You might have been bothered by mistakes that this algorithm have made so far. Another type of classification algorithms is multi-class classification algorithms. In multi-class classification algorithms, there are more than two classes or two labels for our data. For example, suppose we want to build an algorithm, a classifier, that is able to recognize the pictures of animals and label them correctly as to what type of animals they are. As you see here, we have pictures of cats, dogs, ducks, and rabbits. In the training process, each data point X is paired with a target value Y or a label Y, which is also called the classes. So we have paired data. The goal is to teach the classifier how to classify these animals and label them correctly. For example, label a picture of a cat as a cat. In a mathematical context, this means that the classifier has to learn a function f that could map a picture of, for example, a rabbit to a label of a rabbit. Suppose that the algorithm has not seen a picture of this particular picture of a rabbit. So based on the training that it has had before, it must be able to recognize this picture as a rabbit and classify it correctly as a rabbit, solely based on the training that it has had before. If you remember this in supervised learning, every data point X was paired with a target value Y, which was its label. In unsupervised learning, however, the data consists of a set of input vector X without any labeled data or corresponding target values. In unsupervised learning algorithm, the goal is to discover similar groups within the data. This method is known as clustering, or to determine the distribution of data within the input space, such as the density estimation, or to project the data from a higher dimension space down to 2 or 3 dimensions so that we could visualize the data. for the purpose of visualization. In this course, we will be using a Python library specifically designed for machine learning called Scikit-learn to learn about different supervised and unsupervised methods and their different application on real data. Scikit-learn has a very resourceful and useful website that you can utilize to learn about different algorithms that this library has and even access to different examples and even data. So scikit-learn is a Python library that it's built on IPython and it's compatible with other libraries of Python such as NumPy and SciPy and Matplotlib, which makes it perfect for a Python programmer. Scikit-learn is very simple and efficient to use, and it's open source, so it's free. And it has all the algorithms for supervised learning, such as classification and regression, and also for unsupervised learning, such as clustering, dimensionality reduction, and also for model selection and pre-processing in different steps of machine learning when you want to build a model. A little bit about the history and background of scikit-learn. Scikit-learn, interestingly, was initially developed by a guy named David Cornapio as a Google Summer of Code project in 2007. Later, Matthew Brocher joined the project and started to use the Scikit-learn, the library, as a part of his thesis. In 2010, the INRIA, which is the French Institute for Science and Technology, got involved with the project, and the first release of the library, the version 0.1, was published later in January 2010. At the time of developing this slide, the project has more than 30 active contributors. Scikit-learn provides a range of different machine learning algorithms, including supervised and unsupervised, via a consistent interface in Python. It is licensed under the Permissive Simplified Berkeley Software Distribution (BSD), and it is free. The scikit-learn library is built on the scientific Python SciPy that must be installed before you can use scikit-learn. Other libraries that are used in scikit-learn are NumPy, SciPy, Matplotlib, IPython, and SymPy. But if you actually install Anaconda, these libraries are already installed, and it makes your life so much easier. So to summarize, the generally these would be the usual required library that we're gonna use when we want to develop or apply machine learning algorithms. The first one is NumPy, which is based on an n-dimensional array package. SciPy, fundamental library for scientific computing. Matplotlib, which is used for two-dimensional and three-dimensional plotting. Seaborn is another example. IPython, which is enhanced interactive console for programming using Python. SymPy, which is symbolic mathematics. And Pandas, which is a data-based library, data manipulation and analysis library in Python. Scikit-learn is mainly for modeling and not data manipulation. For the data manipulation, we usually use other libraries such as NumPy and Pandas. Some popular methods, group of methods and tools that are provided by scikit-learn includes clustering, for example, which is part of unsupervised learning. For grouping unlabeled data, such as the k-means method. Cross-validation is another tool provided by Scikit-learn, which is for estimating the performance of supervised machine learning models on unseen data. Scikit-learn has a set of data sets built on itself for test data sets, for generating data sets with specific properties for investigating model behavior. Also, Scikit-learn has the dimensionality reduction tool that is part of unsupervised machine learning methods for reducing the number and attributes of our data that it can be used in summarization and visualization, and also feature selection, such as in principal component analysis. The other set of tools included in scikit-learn is the ensemble methods, which is for bundling up and combining the predictive models or the supervised machine learning algorithms to make them more efficient and more useful in prediction. Feature extraction is the other tool, which is for defining attributes in image and text data. The other tool is feature selection for identifying meaningful attributes in a set of data from which we can create supervised models. Parameter tuning is the other tool provided by scikit-learn, which is for optimizing the behavior of your supervised model, make them to make them more efficient, more productive, and more accurate. Scikit-learn also have provide manifold learning, which is for summarizing and depicting complex multidimensional data. And also, of course, a set of supervised models, including a vast array to generalized linear models, discriminant analysis, naive Bayes, lazy methods, neural networks, support vector machines, and decision trees, and many more. Before we move on to a complete workshop-like session in which we are going to do all programming and all coding, I want to give you a general picture of our general guideline in the necessary steps that are common to do when you want to apply machine learning in Python. So the first one is, of course, if you want to utilize the power of the libraries that we know for data processing, data manipulation, and data visualization, and other things, you need to import these libraries. The most common libraries that we're going to use in typical machine learning application includes NumPy, Pandas, Matplotlib, and the scikit-learn sklearn. So you are all familiar with how to import a library. We're going to import using the command import, then the name of the library, and we can actually give it a nickname such as, I'm going to go with this one, import matplotlib.pyplot as PLT. So PLT is the nickname here, and it makes it easier and simple for later on when we want to use an application or a method from the matplotlib.pyplot. So we don't have to actually write this whole complicated, unnecessary name. We can just use the PLT, its nickname instead. The next thing that we need to do, we need to work on data. So we need to import or load data. Data needs to be actually numeric. You may be wondering, how about other types of data, such as graph or images or sounds? Even they have to be converted to a numeric data set, because finally this is going to be a computer. It's a binary system. So at the end, it's going to be all converted into 0 and 1. So all data needs to be in numeric and stored as either a NumPy arrays or a SciPy sparse matrix, or other types that are convertible to numeric arrays, such as a Panda data frame. You can have different sources of data. For example, you can have a data set stored in your local storage, or it can be a data set that is online, or actually is a data set that it's within a library. So there are different ways to load or utilize the data. We're going to learn about these three ways. If you have stored your data in a local storage, you can read it with the pandas read underscore CSV command. So you need to put the address of the local storage address and then the name of the file. It has to be a CSV file, and then read it to a panda dataset here. If your data is within a website, then you can use the address and put it in an URL name, and then use the read underscore CSV to read that the location that your data is stored online. If your data is actually within a library, Scikit-learn has actually a data set. You can import that data, for example, from a scikit-learn import datasets, and then datasets use the command load underscore iris. For example, it's a iris is a dataset. It's a very popular dataset in scikit-learn. I'd say even probably the most popular dataset, which is used by machine learning, especially for the educational purposes for the first time learners. It's very popular. So this is how you can access your data. After reading or importing your data, a common step is pre-processing. The pre-processing step may or may not be necessary. This step actually helps us to prepare the data so that we can get better results out of our model or algorithm. There are several pre-processing actions that could help us to improve the behavior and the results of our modeling and the prediction process. These steps can be including methods such as standardization or normalization or binarization, or even taking care of the missing values in your data, which is actually a common problem, a very common problem when you work with data that is not a standard data. We're going to learn about some of these or most of these later on as we go further into the course. Separating training dataset and testing dataset. In machine learning, the study and construction of algorithms that can learn from data and make prediction on data is a common task. Such algorithms work by making data-driven predictions or decisions through building a model from the input data. The data used to build the final model usually comes from multiple data sets that are going to be from different stages in model application. In particular, three data sets are common. The training data set, the validating data set, and the testing data set. What is the training data set? The training data set is the set of data that is used for tuning parameters of a model, such as weights in some models. The model is trained on the training dataset using supervised learning method. The training dataset often consists of pairs of an input vector or array or a scalar and the corresponding output vector or array or a scalar, which is commonly denoted as the target or label. The model is run with the training dataset and produces a result which is then compared with the target for each input vector in the training dataset. Based on the result of the comparison, the parameters of the model can be adjusted or, as so said, tuned. What is the validation dataset? After the training stage or fitting stage, the fitted model is then used to predict the responses for the observation in a second dataset called the validation dataset. The validation dataset provides an unbiased evaluation of a model fitness or performance on the training dataset while tuning the model's hyperparameters. Hyperparameters are those values set before the learning process begins, such as the number of hidden units in a neural network that we're going to learn later on. Validation datasets can be used for regularization by early stopping. Stop training when the error on the validation dataset increases, as this is actually a sign of overfitting to the training dataset. Overfitting is a condition that in which your model or algorithm is fitted too much or attached too much to your training data set such that is incapable of making prediction outside of this set of data. The next data set is the testing data set. Testing data set is a data set that is used to provide an unbiased evaluation of a final model fit on the training set. When the data in the dataset has never been used or seen by the training session step, for example, in cross-validation, the test dataset is called a holdout dataset. A dataset can be repeatedly split into a training dataset and a validating dataset when you hold out the testing dataset. This is known as a cross-validation that we're going to talk about it later in this course. The test dataset is independent of training dataset, but follows the same probability distribution as the training dataset. If a model that is fit to the training dataset also fits well into the test dataset, minimal overfitting has taken place, which is a good thing. A better fitting of the training dataset as opposed to the test dataset usually points to overfitting. So if your model performs well with your training dataset but performs poorly with your testing datasets, that's an indication and a signs of overfitting of your model to your training dataset. Oh no, oh no. Model building and fitting. At this step, you need to choose a model and import it from the scikit-learn library. The question of which model you should choose is a very important question, but it doesn't have an easy answer. It takes experience, knowledge of your data and the problem that you're working on, and oftentimes try and error to pick a good model. After you choose a model, you need to import the model and feed it to your data. I'm going to show you a general sketch of a set of lines that usually you have to write to do these steps. So this involves importing your model. For example, from the scikit-learn, I'm going to use general names, scikit-learn.xyz. This is the set of algorithms or models in a scikit-learn. Import a particular model, for example, a model. Let's see an example. For example, from a scikit-learn.linear model, this is a set of linear models. Import a particular model, which is linear regression. And next, you need to fit your model into your data. So this is your model, my model name, linear regression, normalize equal to true. This is actually a parameter that we're going to talk about the parameters of each algorithm as we learn about them. And to fit your model into data, you need to use fit xy. Okay, so your your model name, whatever it is, dot fit, and then put in the sample data that you have, which is the training data set X and the label Y. This is going to train and fit your model to your data. Using the model to make prediction. After you have fitted your model to your training data, the training step, it comes to the goal step, which you want to make a prediction using your model. For this reason, we pass the independent variable or data that we have, which is actually the X data, X variable or data into the model so that the model can make a prediction on the dependent or target variable, which is the Y variable, the labels. For example, we can define a, a target variable called predict, Y predict, and then this is our model. Our model, it has been trained already with the training data set in the training step. To ask it to make a prediction, you have to call just predict dot predict and get it the independent X variable so that it actually makes a prediction on the Y variable or Y data set and put it in the Y predict. Evaluating a model. To judge the performance of a model, we need to use some metrics. There are different metrics available to use. Some of these metrics are actually specific to certain class of models. For example, we can use accuracy score to evaluate the classification type models based on the predicted value that your model has predicted and the real value of the target variable or the label variable. Let's see an example. So the command is accuracy underscore score, and then we give it the real values of the dependent variable, which is y underscore test, and the predicted values predicted by your model, which is y underscore predict. So this is going to ask, this accuracy score is going to give you a judgment based on these two values, how accurate your model has been. For the classification models, we can also use classification report, such as the following. So we have to import from the classification report first. From scikit-learn.metrics, import classification report, and then we ask it to predict it, to print it out. Classification report, we give the real values of your labels and the predicted values of your labels. And it's gonna then print out the classification report to a judgment of the performance of your model. There are other models available, some of them specific to certain models. For example, we have confusion metrics, we have the mean absolute error, mean squared error, we have R2 score, and many more that we're gonna talk about it later on in the course. Some of these metrics that I mentioned, you are already familiar with them based on the regression topics that you have learned in, for example, in your statistics class. For example, the mean absolute error or MAE or deviation is a metric that you already know from statistics. So MAE is equal to the summation of the deviation from your real values and the predicted values, and then finding the average over them. By the way, this is, if you remember, the deviation of your predicted values from your real value is the error in your model. The other one is the mean squared error or MSE. MSE, instead of finding the absolute value, it finds the square of the error that you have and then find the average of that. Also, you might remember the R score. The R squared. The R squared is 1 minus the summation of the deviation of your predicted value from your real value squared divided by the deviation of your average value of y values from the each y value squared. So this value is going to give you the R squared. Our first machine learning algorithm. It's time to apply our first machine learning algorithm. We're going to start with an easy one. It's called the k nearest neighbors, or KNN. We will talk about this algorithm in more details in future. For now, let's just apply the algorithm on a sample problem. Before we start, let's review the components of machine learning algorithm, the three components. The three components of every machine learning algorithm. Every machine learning algorithm has these three components. First, representation. It's a way to represent knowledge. How to represent knowledge? The type of algorithm we mean. Choose a feature representation. Next is evaluation. What criterion we should use to evaluate the performance of our algorithm. And next is the optimization, or finding the best setting for our parameters so that we can control the performance of algorithm for the better. What is the best settings and tuning of the parameters for the best performance? We first need to specify and define a task or a problem for our machine algorithm to perform and to do or to solve. We have a set of data that consists of features or attributes for some fruits, including attributes for apple, lemon, oranges, and mandarin oranges. What we would like the machine learning algorithm to do is, given the features of a fruit, the algorithm has to identify what fruit it is. So it has to give it a label, and we want it to be able to give it a correct label. Feature representation for fruits. We need to identify and define some features for fruits that help the algorithm to distinguish them from each other, right? You can think of, for example, the size of a fruit to be different from each other. So, for example, the height, the width, or the mass of a fruit can be features of fruit. Also, the color of fruit, which is more a quality than a quantity. So we need to find a way to quantify the color, which the creator of this problem, they have already done it. We're going to talk about it later on. So these are the features that we have picked. So you see here we have put this in a structure, in a numerical array, understandable into the computer setting, algorithm setting. The first array that you see here is the label array, or the target value. You see that we have, for this specific example, we have the fruit label as 1, fruit name as apple. So we give apple the label of 1. Just it's arbitrary, it doesn't have to be 1. We can create another label. We could have given it 2, but we haven't started with apple. And the fruit subtype is crisp pink. So these are the label, the y values. And then the second array that you see here next to this is the features of this fruit. We have the mass, the width, the height, and the color score. These are the features that we have picked to distinguish the fruits from each other. The mass for this specific fruit, which is an apple, is 158. Width is 7.4 and height is 7.2. And for the color, which is kind of reddish, we have put a score instead. So as I said, the creators of this example, they have come up with a way to quantify the quality, equality, which is color. Color is quality. And showed it with a number here. I'm going to show you actually how they have come up with this. It's very simple. They have a way to do that. That is very easy to understand. So we're going to give this set of data from our sample data in the training session to our classifier or machine learning algorithm. And then the algorithm is going to learn this, and later on when we give such a specification or feature to the algorithm, it would be able to understand and predict that, okay, this is going to have to be an apple. So its prediction is going to be an apple. And then we can use the algorithm for some fruits that the specification or the features of that has not been in the input data for future prediction. The fruit data set was originally developed by Dr. Ian Moray at University of Edinburgh, but the dataset that we use is another version of this dataset that was revised by Dr. Kevin Collins Thompson from University of Michigan. He actually added another feature to the dataset, which is the color score. Let's take a look at the sample fruits and the features. We have apples, and the features that the dataset has are the width, the height, and the mass, and also the color score that was added later on by Dr. Thompson. Also, we have oranges, we have mandarin oranges, and we have lemons. So these data, the types of fruits, the label, and also the features of them have been put into a data set, a numerical data set, as you see in this table. So this table of data or array of data includes both the labels and the features. But we only need actually one label, and we're gonna use the second column, which is the fruit label, as our label. And the last four columns are the features that we're gonna use in our machine learning algorithm for prediction. This data set is uploaded on Camino, and you can download it and follow along with me in coding and developing and applying the machine learning algorithm as I go through later on. The color score feature that was added by Dr. Thompson is based on a simple idea, but it's not actually easy to quantify a qualification here, which is actually color is a quality here. So Dr. Thompson has said this transformation of color to codes. So we have for different colors, we have different codes here, starting from 0 to 1. So it's going to be a value between 0 and 1. Red is going to be from 0.85 to 1. Oranges are from 0.75 to 0.85. Yellow is between 0.65 to 0.75, as you see here. And greens are between 0.45 and 0.65. And since we don't have any fruits in bluish or pinkish, we don't have them here. Credit to Dr. Thompson for this feature. So I have put all the data, I have downloaded all the data, the IPython file template and complete, and also the fruit data with colors, the input text data file in a folder, which you actually can access it through your Jupyter node. So if you go to, and if you open up your Jupyter, Anaconda and then Jupyter, and then go through and find exactly the folder, it's going to show all the file that you have. And then you can open up the template file to follow along with me. And since the food data is also in this folder, you don't really need to upload it to your workstation or workspace. So let's get started with importing libraries. I'm going to import the libraries that we need. We need NumPy as MP, import pandas as PD from matplotlib, import pyplot as plt. Okay, everything looks fine. Here we want to import the data. The data file is fruit underscore data underscore with underscore colors dot text. So let's read it to and put it on a variable. I'm going to call the variable my fruits equal to, I'm going to use the panda read table and then the name of the file. You don't need to put any address of your local storage because this file is in the same folder, so it's gonna hopefully work. So let's see. It works. All right, now that we imported the data and we have the data, let's print out the head of data to see some of the data. So I'm gonna ask for the head of the data. So these are the head of data. We have 1, 2, 3, 4, 5, 6, and 7 columns, and it shows the first 5 rows of our data. As you see here, we have fruit label. Label 1 is for apple, label 2 is for mandarin, and etc. We don't see the other fruits yet. Fruit subtype, we don't care about this much. And then the features are the last 4 columns. We have mass, we have width, height, and color score. All right, let's see how many items or fruits we have and how many features we have using the shape command. So we're going to use the shape command here. My fruits dot shape. Okay, so we have actually 59 data sample or fruits, and for those fruits we have the 7 columns, of which 4 of them are features. As you see here, we have 7 columns. Here we only saw 5 of them, so totally in the data set we have 59 fruits or data points. All right, let's now dive deeper and take a look at the whole data. So I'm gonna print out just my fruits. My fruits. All right, this is the whole data. As you see here, we have the 7 columns here, and '58. We have lemon, we have oranges, and apple and mandarin. The next step is to split our data into training set and test set. The training test set is used to train our data to learn about the hidden relationship, figure out the relationship between the independent variable x and the dependent variable y, which is the label. And then after that, we're going to evaluate the performance of its prediction on the testing set. So you see here that we have, this is original data set. We have the x variable, which is the independent variable that includes our features such as the height, width and mass and the color score. And we have the y variable, which is the dependent variable that include the target value that is actually the fruit labels. So one stands, for example, for apple. So we want to use the train test split function from scikit-learn model selection module to split these data into two sets, training set and test set. These training set and test set also gonna have their x variable and y variable. The x variable for training set is called the x train, and for the test would be x test and y test. You can specify how much of your data would you like to put into training and how much of it would you want to put on test. If you don't specify that, by default, it's 75% of your data is going to be split into training, and 25% is going to be for the test set. All right. As you see here, we use X for the feature variables because it's going to be the capital, and because it's a set of different features. It's not just one value. It's a height, width, and so it's more than one. Unlike Y, which is only the label of the fruits, which is 1, 2, etc. So we use a small for that, and because it's just a scalar. All right. Let's now go ahead and try this in scikit-learn. Let's split our data into training set and test set. For that, we need to import the train test split function from the scikit-learn model selection module. So from scikit-learn model selection, import train test split function. Okay. Now I want to create the dependent variable and independent variable. The independent variable is going to be our features, a set of features. We're going to only use the three features, the mass, the width, and height, and we're going to use the color score only for visualization. And since X is going to include more than one value, so it's an array. That's why we show it by capital X. So X is going to be my fruits mass, width, and height. Okay, and we have one label, and that's actually the fruit label. I'm gonna use that as our target value or label. And if you look back to this, you're gonna see it. Okay, so we have fruit label. For apple, we have 1. For mandarin, we have 2, and etc. So this fruit label is going to be our only target value. So y is going to be only one value. It's a scalar and not array. So that's why we show it by small y and not capital Y. So y is going to be my fruit label. Okay, it works, it's fine. Now let's split the data. We're going to use the split function and put the data into training and test. So for training, we have the X training and Y training, and for test, we have X test and Y test. So X train, X test, Y train, Y test. So X has to be in capital and Y has to be in a small letter, equal to the function train test split, and then we're gonna input our data X and Y, and I'm going to use also random state 0. If we do this, all of us would get similar output. So if you don't use this, each one of us would get different splitting. Let me run this. Okay, it looks fine. All right, let's now see the head of our X train. It has already been split, so we can now see it. So X train and head. So this is the 5 number. As you see here, it randomly has selected these fruits, the 42 for the 8th one, the 7th one, the 14th one. These are all random, and the 3 features that we wanted. So let's also take a look at the X test head, and this is also randomly selected. Y train, we can also look at it. Y train head. So this is only a scalar. That's why we only have one column here. These are just indexes. So this is the fruit label. One is for apple, if you remember. And we can also see the Y test head. Y test head. And this is also one column that shows the fruit label. All right, so it has been. Next, we want to plot our data into a very neat 3D feature scatter plot. This step is not necessary, but it's a fun step to do to see the power of Python. So we're gonna get this 3D plot almost the same as this one. So let's see. Let's put it in, see it in how it works in Python. All right, now we want to visualize our data in a 3D feature scatter plot. Since this is going to be a little bit more advanced for you, I have left this part of the code for you in the template so you can just run it to see the output. If you run it, this is the 3D plot that you're gonna get. So here we have the width, the height, and the color score, and different fruits are shown by different color here. All right, we are finally there. We want to apply a machine learning algorithm. We're gonna apply KNN specifically. KNN algorithm is a classification algorithm. KNN stands for K nearest neighbors, and the algorithm works based on the idea of majority of votes of the nearest neighbors of a new data point that you want to identify. So we need to actually have a metric for what do we mean by nearest. So we need to define that. We're going to talk about in more detail later on in the course. So for now, I'm just going to give you a brief description of how this algorithm works. So suppose that we have a data point here that we don't know what it is, but we have, for example, stars here. We have stars here, and we have a square here, a square here, and a square here. Okay, and we have, for example, a heart here and a heart here. So if we define, for example, the two neighbor here are important, then the two closest neighbor to this unidentified object is these two stars. So it's going to identify this as has to be an star. Okay. If you consider the number of neighbors as, for example, 5, then the closest 5 object to this is going to be this 5. And here we have 2 stars and we have 3 squares. So 3 is more than 2. So that means that this is going to identify this object as a square. All right. So that's enough for now. Let's go ahead and get a start coding in Python. Applying a KNN algorithm. Let's first import the KNN algorithm. So from sklearn neighbors module, neighbors import. The name of the algorithm is kneighbors. neighbors classifier. Make sure that you follow the correct spelling of capital or small letters. I want to make our life easier and import this as KNN. All right, and now I want to specify how many neighbors do I want. And neighbors, number of neighbors, number of neighbors, number of neighbors. I wanted this to be 5. We can change this parameter later to control the behavior and accuracy of the algorithm later on. Now I want to create a KNN object. So I'm going to call it myKNN. MyKNN is a copy of KNN with the number of neighbors that I have defined, which is 5 for now. So it runs finds. Okay, the next is now we have the algorithm. We have the algorithm. It's called myKNN. This is our algorithm with the parameters that we specified for it. The next step we need to do, we need to train our algorithm. So we're gonna supervise or train the algorithm on the training set that we know the labels as well. So we know the features and we know what fruit those features have. So to train our algorithm, we're gonna use the fit command from the Scikit-learn to do that. So fit my algorithm or train my algorithm on the training set, X train and Y train. Okay. So it runs fine. And we have, as you see here, the algorithm, k-nearest algorithm, it has a lot of other parameters. We only worked with this one, the number of neighbors we specified with 5. Others we didn't specify, so it automatically specified by itself. Later on, we're going to learn about other parameters as well. Okay, so the next step is to estimate the accuracy of the algorithm now that it has been educated or trained. So to do that, we're going to use the testing set, and we use the score to give us the accuracy. So let's do that. Let's find the accuracy. So I'm going to ask myKNN score and give it the testing set, test and y test, and run it. The accuracy score on the test data is 53%. The closer the score to 100%, the more accurate our algorithm is. So this is a little bit better than 50%. It's like tossing a coin, a little bit better than tossing a coin. All right, if we actually change the behavior of the algorithm, we can change the number of neighbors. For example, let's go with 1. We need to rerun all of these codes. So run this, train train our algorithm, and then find the score. So the score now is 59. If we do this with, let's change this, for example, to 7 now. What is the score? 53. So by changing this parameter, we can change the accuracy of the algorithm. After training and educating our algorithm using the training dataset and getting estimation of its accuracy performance using the test set, now it's time to ask it to make a prediction on a new data that we don't know of. Okay? So we have an unknown fruit. We know its features. We know that its mass is 20 and its width is 4.3 and its height is 5.5, but we don't know what fruit it is. Okay, so we want to ask our algorithm to help us. So I'm going to create a variable here so that the algorithm can make a prediction and put it in here. I'm going to say, call it fruit prediction, for example, prediction. So, and then I'm going to call my algorithm, KNN, and ask it to predict this unknown fruit to see what fruit it is. Okay, the command is predict. We have to give it the unknown fruit features, so I'm gonna put it here, the unknown fruit. All right, it finds now. Now we can print out the label that our algorithm made predictions based on the features of unknown fruit. It is stored in fruit prediction. We can now see the output. It is actually 2. The label is 2. We don't know what 2 is, so we have to go see what is 2. So 2 is, if you go back to this table, 2 is actually for mandarin. So our algorithm predicts that this must be actually a mandarin. But it's not easy to each time go back to the table to see what label is for what fruit. So I'm gonna use this little piece of code that you already have it in your template to help us decode the label of the fruit. Okay, so let's run it. It says it's a mandarin. So each time we make a prediction for a new unknown fruit, we can use this give me the fruit name to decode the label of the fruit and gives us the name of the fruit. Okay, so let's try another unknown fruit. So we have another unknown fruit. We don't know what it is, but we know its feature. So we're gonna ask our algorithm to make a prediction for it. So fruit prediction equal to my knn make a prediction, predict, and using this unknown fruit, and then I'm going to use this, give me the fruit name, copy it here, here, to give us the fruit. It says it's a lemon. Okay, so you can actually play with this algorithm. You can give it an unknown fruit, its features, and then make a prediction using the algorithm. So feel free to go ahead and play with this algorithm and learn more.